So this is called a DEQ Stem. It's usually a crossover between A, B, and BC. Sometimes BC will have like an additional question attached to theirs. A lot of times there's a slope field that goes with these as well. I didn't put that on here because that's going to be another day. We're going to take like 15 minutes and review slope fields. But this is a super FRQ. It obviously has more parts than you would have, so I tried to hit everything. The first thing you should always do, as you guys kind of are getting used to, is you really need to not just read the stem of the problem, but understand the situation. Sometimes they're easy to understand. Sometimes, like in BC, we did one the other day about, was it plankton? Yeah, and it was the stem of the problem was really long, and they were like doing this density of plankton beneath this like observation ship, and it was like took a couple reads through the stem of the problem, even for me to be going, what is going on with this problem? This one, it's pretty easy to understand. We've got watermelons come in season, and a warehouse is receiving the watermelons, strictly increasing. I would underline or highlight that. It means that if they tell you something, it means you're going to use it. A lot of times when I see strictly increasing, I think, oh, they might ask me a Riemann sum. Okay, they actually don't in this one, but that's kind of what pops into my head. I will need that though for something. They tell me it's twice differentiable, which means it's also continuous. So in my head, I think maybe they're going to ask me an existence theorem, so I know that the hypothesis was met. W is the total amount of watermelons in the warehouse. So I like to, with these, just draw a quick little picture. W is the amount of watermelons in here. Maybe I should make them green. Right? Let's make it realistic. There, do they look like watermelons now? No. Okay. Well, jelly beans. Alright, so those are the watermelons in the warehouse. And it says that, let me erase this. This is dW dt, which is the rate that watermelons are going in. They aren't being taken out because it says W is strictly increasing. So the number of watermelons is going up over time. Its rate of change, the rate at which they're entering, is unique because it's a function of both the independent variable and the dependent variable. So like if this was dy dx, it's a function of x, which we're used to, and t. So it's and y. So it's a little bit goofy. Then they give me an initial condition. That leads me to believe I'll probably be solving this and have to find Carl, or I'm going to do an equation of a tangent line. I haven't read this since last year, so I'm telling you what I think as I read the stem. So I'm going to write that point down so I know that I have it. This would be t. This would be the number of watermelons at that time. All right. Oh, there it is right off the bat in part A. I knew when they give me an initial condition, it's either to get me a point on that graph to walk in, or a way to find Carl, right? So when I read this, it says write an equation for the line tangent to the graph at 2 weeks. We've done that a zillion times. So I've always said you need a point, and you need the slope, which would be dW dt at that point, which is going to equal twice the t value, so 4, times W minus 9 times 1. So really what that means is at 2 weeks, the rate of watermelons is changing at 4 watermelons per week. It seems like it should be hundreds of watermelons. That's not very many watermelons, right? That's a very slowly increasing warehouse. Here's a watermelon, then wait 24 hours. Here's a watermelon. It's a very slow rate of change. Anyway, let's go write our tangent line equation. It's y minus the y I know is equal to the slope, which is the derivative, times x minus the x I know. If you can't write an equation for a tangent line right now, that would make me really nervous. You can leave it like that, but I like to go back and say, well, my y is really w. So the number of watermelons will equal 10 plus 4 times 2 less than the time. I like to go back. They honestly will take both forms, green or black. I like black because it gives me context. Like, well, what is this? It's giving me watermelons. All right, so I have this strictly increasing watermelon function that I call W of t. I don't know if it's concave up and increasing or concave down and increasing. I'll figure that out maybe in another part of the question. But I'm going to make a fake increasing function just so you see what's going on with your tangent line approximation. You knew that at 2, there were exactly 10 watermelons. We hopped on here, and now it says use it to approximate how many there are at 3. So what I need to do is I'm going to hop on that tangent line at 3. So the amount of watermelons at time 3 would just be 10 plus 4 times 3 minus 2. So just 14 watermelons. It asks if that's an over or an underestimate in part B. We should know that that involves concavity. Now this is where this one gets a little weird. It wouldn't be weird if it was back and it was just x and y and I said find the second derivative. You know you're doing kind of implicit, but this is, I'm going to write my original down right here. This is kind of the kicker question, and it's been happening quite a bit in the last, I'd say, 5 years, where they've taken these contextual problems and had you find a second derivative where it's either just in terms of the top variable or both. Taking the second derivative of 4x squared with respect to x is a no-brainer, right? But when you have a contextual problem, I would write out what it means. I'm taking the second derivative as time changes of dw dt. That's where the d squared w, that's where the notation comes in. I've talked about that. That means on this side, I'm taking the second derivative with respect to t of twice t times w minus 9. I'm actually writing it out because I think it'll help you. All right, so I actually have to know how to take this derivative. This one's kind of interesting because this is a product of two functions, one of time and one of watermelons. What rule do you think I'll use now? Product rule. It's just going to be a little funky, right? It's like taking a derivative with x's and y's. The derivative with respect to x of x squared is twice x. The derivative with respect to x of y squared is twice y times the derivative of the dots, dy dx. Okay, so we're going to have to be careful. So I'm going to do first function, which is 2t, times the derivative, and that's where I like this notation, of the second function. That's first d second. I'll wait to do that. First d second plus second, w minus 9, times the derivative of the first. Well, this is like, with respect to x, what's the derivative of twice x? There's a variable match, correct? It's actually 2 dt, but that one's just 2. Okay, so that one's not too bad. It's this guy, kind of the reason why I'm covering it. This guy, I want to make sure you know what that is and what to do with it. What's the derivative of the constant no matter what? Careful. 0, right? Constants don't change as anything changes. The number 5 is 5 even if time is increasing, right? Doesn't matter. But, so this guy's going to go to 0. What's left is just dw dt. It's not dt dt, so it's not a 1. If this was a t right here, 1, correct? So you have to be careful because my first function is twice t. My second one ends up being dw dt. What do you think I'm going to put in for that? EBers, you should be, we've done this a couple times in the last month. So when I know that this ends up being dw dt, Owen, what do I actually put in for it? The original, yeah. So we did that with the bird, we did that with the potato, and one other one. So that's my first d second, and then this is my second d first. So it's a little bit goofy. There it is. Now it asks me, so that's my second derivative. And again, yours wouldn't be that involved, but this is what I call a super FRQ. So it says find d squared w dt squared, the second derivative, I did it. Use it to determine whether my approximation from part A is an over or an underestimate. So what I know is I have this strictly increasing function. It was either like that or like that. So my line was either underestimating or overestimating, correct? So what I do is I go back here and I have to decide, is this going to be positive in that area? You might say, in what area? When t is 3. That's where I want to find out the concavity right next to t equals 3. So when t equals 3, positive, positive, correct? Also, it said that at time 2, there were 10 watermelons. It didn't say at time 3, but now in the stem of the problem. What's going to make me very assured that W minus 9 is positive? Yeah, W is strictly increasing, correct? So I know that this guy right here has to be positive because we're increasing. And then from 2 weeks to 3 weeks, I have to go from 10 to something bigger than 10. Does that make sense? So I'm 100% sure this is greater than 0. However, that could be a guess. So you might want to put, because T is greater than 0, 3, I can see that, and W is greater than 10. Just like what you said, Ty, I would phrase it that way. So now I know that my watermelon function, not only was it strictly increasing as concave up and increasing, correct, Bethany? So was my tangent line giving me an over or an underestimate? Under. Yep. So you should reference that here. If you just write underestimate, that could be a 50-50 guess. So you should say since W is concave up, this is an underestimate. And I'm not going to write the whole thing out, but that's a tricky thought process. That second derivative, when it's kind of contextual and not just like if I were to say, hey, Lainey, what's the derivative of x squared? She would just go, well, first d second, you should probably call that a y prime, right? Plus second d first. That's really what we did. But we did it with w's and t's, and you have to know who kind of is the x and the y. All right, so next step, it says, what is the rate at which watermelons are being added? So it's not about watermelons. It's the rate that watermelons are being added. So really, that's a question about the second derivative, right? dw dt is the rate at which we're adding watermelons. They want the rate of that rate. So all we need to do is go back to our answer, which I erased. No, I didn't. All you have to do is go, well, I need to find the rate, that rate is changing at 2 weeks, and then I know t is 10, because they told me that in the stem of the problem, and I have to go put it in there. But I don't want to. It'll be a nice whole number, easy to find, correct? But then it says, explain what it means in the context of this problem. Well, our original was rate in watermelons per week, and we took its derivative, right? So it'd be the rate, that the rate of watermelons is changing. Its label would be watermelons per what? Week per week. Yeah, it's kind of goofy. All right, then it says, under what conditions would W, the original function, this guy, have a critical value? Critical values occur when the rate or the derivative is equal to 0 or does not exist. That's what you need to find. And they gave you the equation for that. It was 2t, all right? So it was 2t times w minus 9, correct? That exists everywhere, and time is positive, obviously. So what's my critical value? At t equals 0 or what? W equals 9, right? That's an easy question if you know what a critical value is. A critical value on a function is where the derivative equals 0 or doesn't exist. So that would be at t equals 0 or w equals 9. My guess is you wouldn't need to put t equals 0 down because that doesn't really make much sense. Okay? The next one I want to go to is, it says, is the rate at which the watermelons are being added to the warehouse increasing or decreasing at t equals 2? That would depend on what we got for part C, right? If we got a second derivative that was positive, which I think we would have, because we would have put in a 2, a 2, a 10, and a 10. That would have been greater than 0 there, correct? So when it says, is the rate increasing or decreasing, we got a positive second derivative. So the rate was increasing. The first derivative was increasing, so the second derivative was positive. That's an easy question. This one is the one I want to do. This says find the particular solution to W of t. Bam. Which means we're not going to guess. We want a function or W. I made a fake W because I knew it was increasing. I knew it went through 210. I also then determined it was concave up, so I made this fake function, correct? But I couldn't it's just a fake graph, and we hopped on here and we said, oh, that's an underestimate. Now it says, what is this function? So what skill do we use to figure out what W was? This is separation of variables. Yeah, you know you need to integrate to get from the rate back to the original function, or from f prime back to f. To remove a rate, you integrate, but you can't integrate with mixed variables. So you're going to separate this. You're going to go 1 over w minus 9, keep all things top variable on the left, and then we're going to go to t dt. So this is a good set bar, which I don't know that we're reviewing much anymore because it's the most recent. So we integrate, and then do you guys remember what the antiderivative of w minus 9 is? Natural log, right? But be careful, because on last year's AP exam, which ABers, you're going to be looking at the 2021 one like this tomorrow. Theirs had, I don't remember, it was like that where the variable was being, oops, sorry. It was like this last year. It wasn't W's and T's. I can't remember what it was. This is still natural log, Natalie, but do you remember the difference? It would be the natural log of what? That, and then what? Negative correction. Yeah, and if this had been a 2, it'd be a negative 1/2. You're used to that from our partial fraction decomp. It happened all the time. But ABers, watch out for that. This should actually be in absolute value bars. All right? And then over here we get 2t squared over 2, which is just t squared plus c. Then we need to undo our natural log, so we'll do e to the natural log of w minus 9. And then we'll do e to the t squared plus c. I get to drop all that, correct? And then, do you guys remember in AB how we took care of, do you remember, Cage, how we took care of this situation over here, the e to the t squared plus c? Yeah, like we did something. Anyone, do you guys remember? You remember, Bethany?
You do like e to the t squared times.
Yeah, it's really e to the t squared times e to the c. And what is e to the c? Just what? Some constant, correct? So we're able to write this as c e to the t squared. And if I were to take off the absolute value bars, then it becomes plus or minus e to the c. But that's still just another constant, so it will work itself out. So I'm just going to go like that. So then I'm just going to add the 9 on over. I get w equals c e to the t squared, and then I have a plus 9 here. Am I done? Because it's been about a month for 8 years since we did our step, maybe a little more. What's the last step of these? Owen, do you remember? Find C using the initial condition. And was the initial condition 2 went in for T and a 10 comes out for W, right? So I'm going to indent for that. I'm going to put a 10 in for W. I'll do a C e to the 4th plus 9. And so it looks like I have 1 has to equal C e to the 4th power, which means I have to divide by 1. So 1 over e to the 4th has to equal c, or you could call it e to the negative 4th. You do you. Okay? It's all correct once it goes to a number. So I just need to create some more space over here. So it looks like I have my w equals 1 over e to the 4th, my c, times e to the t squared plus 9. That's not how you'll see it on the scoring rubric, but it's correct. Okay? Like you've seen enough of these where you know they're going to call that e to the negative 4th, right? And then they're going to call this same base, you add the exponents. So they're going to, in the scoring rubric, it'll say e to the t squared minus 4 plus 9. But it's all good. So I would quit up here if you're not comfortable manipulating things. Now it says to use it, for part G, it says for the particular solution that we just find, evaluate W of 0. That would be the amount of watermelons at time 0, which would mean before we started bringing watermelons to the warehouse and they started to increase, how many were there? Well, I have e to the t squared minus 4 plus 9. And I put a 0 in for t, so it looks like I'd have 1 over e to the 4th plus 9. So just slightly over 9 watermelons. That's kind of weird. But we're done. That's it. That's all I know. All right. So there are, by the way, those of you here, it means you're kind of interested in getting that score to probably at least a 4 because you guys are all at 3s or better right now. So if you're continuing to be interested in that, I'm going to show you where I got this from. Because there are 4 of these and we won't get to, we did the graphical one. Remember a couple days ago we did the all graphical STEM A-Bers as on the back board. But in our daily slides, I have it all the way on out, so we're only here on Tuesday. But if you take it all the way on out to when the test is, so it's on a Monday, the 9th, this last slide has these common stems. We've done the graphical in class. We just did the DEQ, the differential equation one. I don't think I'm going to get to these other 2. So these are very, do you know what I mean by stems? Like particle motion's common, but you guys are good at it. The area volume's common, but we just did it yesterday. These are very common AB stems. The other one is rate in, rate out, but that's its own day coming up. And it's its own Elk TIme. I think it's my Thursday Elk TIme is the same, and that's a crossover. You're good at rate in, rate out, though. The escalator, the bananas. Yeah, I think you're good with that. The other thing we never are going to get to is the reviewing of Unit 7. We're going to do Unit 4 tomorrow, but anyhow, A-Beers, it's a Delta Math Quest, 10 questions with corrections today. So you can correct up to 100% if you choose.